The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
This is my second lecture on the example, the model of graphs and networks. Really perfect, beautiful model for the whole framework and important in itself. I guess one thing I did, a major thing that I still have to do is discuss A transpose. See how A transpose just naturally appears in the balance law. So this, Kirchhoff's current law, KCL, it's just like a model for balance equations. By balance, I mean in equals out, essentially. Flow in equals flow out, because we're talking about steady state. So at each node, at node 3, for example, well, let's see, I have 3 edges. So the law, Kirchhoff's current law at that point is going to tell me that the flow W2 plus W3 minus W5 would be 0 if there's no current source, or if I'm feeding current into there, some current F3, then it would match F3. So maybe having just said those words, let me just say W2, I'll say it again, W2 plus W3 minus W5, and I'm hoping I'll find that in the third column here, and I do, because I'm thinking, and we'll write it down, I'm thinking to take A transpose, so it'll be the third row, and here I see the W2, W3, and minus W5 that will show up in the third equation there, the in equals out at node 3. Well, I'll write that down because it's, so 2 or 3 jobs for today. And then Monday, I plan to spend a part of the lecture and all of the review session in review. Kind of, it's a great chance to go back to the things we've done and collect them, assemble them, organize them, and see them again. So that's my goal for both sessions on Monday. And questions then about every aspect. So before I get to A transpose, this part I had written down last time, and there's a little more to say. And what I was saying and want to continue with is the source terms. I put in this B, but I didn't draw anything on the network. So let me draw what these B's represent. So these are, this second lower row is about edge equations, edge variables. So those batteries B are on the edges. And there will be, B has length 5. There are 5 edges. This is a vector of length 5. This matrix A, you remember, was 5 by 4. It produced from 4 inputs, from 4 potentials at the 4 nodes. A produces AU, 5 potential differences. So those are the differences in potentials, but then also there can be source terms from batteries in the edges, and the minus sign is there because I'm talking about voltage drops. So when I say differences, I'm really speaking about voltage drops because that's the way current flows. Okay, shall I okay, this is a moment that I hate. Putting the batteries in. I think you draw a battery with a long and a short. Is that right? Yeah. And then you put a plus and a minus. Well, can I just say, life is too short to get this sign right. You may say, when my car battery stalls, how do I, because it's important at that moment, right? When you start it up, you're supposed to put the right battery, the right lead on the positive and the right on the negative, or you blow yourself up. Okay, so what's my solution? Because I literally refuse to deal with these signs. So my solution is call AAA. Okay, they're paid to blow themselves up. They can do it. So this is serious now. I don't want to be asked about these signs. And I forgive you for messing up the sign. So possibly that's plus, possibly minus, I don't know. But there's a battery in there of length B1, of voltage, 9-volt battery, B1 would be 9. And depending how it was placed in there, the B here would be a +9 or a -9 in the first component. And then if I had another battery here, a B that's on edge 4, there would be a battery B4, and that would show up there in Ohm's law, because Ohm's law will look at the difference in these potentials, but then it'll also account for the battery, right? The voltage that comes from the battery, and somehow combining the AU, which is the difference in these guys, with the B4, I'll know what is the voltage drop across the resistor. And that's what Ohm's law applies to. Ohm's law says the voltage drop across the resistor times the conductance. So this is Ohm's law, that on that edge, the voltage drop across the resistor times the conductance gives the current. So that's the physical law. Is that okay? For batteries. Now a comment on current sources. So what's with current sources? How would I draw those? Well, very often, maybe I might draw a current going into node 1. So that would be an F1 that goes into node 1 and maybe comes out at ground. So that would be a typical F. That would if I imposed a current source, if I send a current source through there, it would go down and come out at ground. And our question is, what are the currents in the 5 edges? What are the potentials at the 4 nodes? Well, I'm making this one ground, so I'm grounding this one to be U4 = 0. And you remember, of course, why I had to do that, because this matrix A transpose A as it stands is, what's the matter with A transpose A as it stands? It's singular, right. And as looking ahead, just a small comment, that this will have exactly the same thing in so many other applications. In big finite element codes, you produce a stiffness matrix that's initially singular, and then you impose the boundary conditions. That's the efficient way to do it, is create the matrix first. That's the big job. Then impose the boundary conditions. That's the small but occasionally tricky part. Now, I indicated what happened here. When U4 was 0, that means that A times U, the U4 there, the 0 is multiplying this, is not unknown anymore. It's known. And so that column is not really any more leaded in A transpose, in A, because U4 is gone from my list of unknown potentials. Okay, now, at the same time, when I went over to A transpose A, I'm making this comment because there were several good questions about it. I claim that also that row coming, which of course comes from the 4th row of A transpose. The 4th column of A is gone, so the 4th row of A transpose should be gone. And we might just think, why is that? What's going on? Of course, it produces exactly what we want. It leaves us with a 3x3 matrix that's not singular anymore. I've removed that 1, 1, 1, 1 from the null space by fixing a potential. Of grounding a node, and the problem becomes just what we want. And I'll write down the equations when I get the Kirchhoff current law to complete the loop. Now, what's going on? Let me remove this current source just so we focus on what I'm speaking about now, on this type of boundary condition. This is like fixing a support, right? It's like fixing a support in our spring mass problem. Can I squeeze in a little spring mass problem? So I have a spring, and then I'm fixing this displacement, U4, to be 0. Now, I want to try to think through what happens in the balance equation, A transpose W, let me make it A transpose W equal F, because that's the case with right-hand side allowed. And now what happens when I fix this? I'm asking you to think back about the force balance, which we certainly saw was an A transpose W equal F business. And then parallel will be the current balance at that node. Okay, so what was the deal on force balance? A transpose for this, with this fixed end here, what was the thing with A transpose at that fixed end? We did not write the equation A transpose W equal F at this point. We did not write the force balance equation at that point. That when I fixed U4, in this case it was the displacement, so I'm fixing it at 0 displacement. I didn't have a force balance in the A transpose part at this node. Now you could say, why? Because, of course, forces have to balance. But what's going on? What's really happening here is I don't have to write out, the displacement here is known. It's not unknown. Well, let me say it in a sentence. Force balance does hold because the support supplies whatever force it takes to balance the internal forces. So, in other words, let me say that again. The force balance will hold, and it will tell me, after I've solved the rest of the problem, it'll tell me what the support has to supply, how much force the support is actually supplying. It's a reaction force, it would be called. So a reaction force is whatever the support has to do to fix that displacement. And so I solved the fixed problems for all the other displacements and all the spring forces. And then I could come back at the end and say, okay, what was the force in that spring, and therefore how much is that support? What's the force being supplied by that support? See what I'm saying? That the force balance at this node comes afterwards. That equation is like knocking that one out of this problem. And it would be the same here. I fix the potential at 0. I fix ground at 0. Current flows. Maybe I might fix that potential at 1. I fix that potential at 0. Current flows. Okay, so I find out, I compute what they are, and this row and column will be gone. Find out what they are. At this node, what's happening? What's happening to the balance of currents? Does this current have to balance that current at the ground? No. The ground whatever current comes here plus whatever current here, comes here goes into ground. Do you see the point? That the Kirchhoff's current law, the balance of currents, the in equals out, is true, but it's not an equation I have to solve in finding the currents. It's something I can discover at the end. I can say, okay, how much current flowed from ground? And similarly up here, if I fix U1 to be 0, then I don't want to fix it to be 0 too. That would be a way to make very little happen. Let me fix U1 to be 1. So this is a standard important problem. It's like, what's the resistance in the net? What's the net sort of system resistance? If I fix this at 1, fix this at 0, some current will flow. It'll come out here. And that'll be the current going into here. Somehow there'll be a balance there and a balance there, but it's found later, just the way the force in the support is found later. Okay, that takes a little thinking. I just wanted to sort of, because I had blithely knocked this row out, and you could do it on the basis, well, if you knock out this column of A, then you're knocking out the row of A transpose, and therefore A transpose A will be 3 by 3. And it'll go down to 2 by 2 if I fix that potential. And if I don't fix it at 0, if I fix it at 1, then something will move to the right-hand side of the equation. Okay. That's that point, I hope, at least discussed. Now, so now we have the whole pattern here, except that I really have still to justify the fact that it truly is a transpose, the transpose of that matrix that comes into Kirchhoff's current law. I guess in the first minute of the lecture, I looked at that particular node. Let's look at all the nodes. Let me look at A transpose W equals 0. Okay. So I'll copy A transpose because I truly believe that Kirchhoff would want me to do it. Okay, so that becomes a row. That becomes the next row. Of course, I see 3 guys going into node 2. Then the one that I looked at before, that's the 3 edges that meet node 3. And then the last one, let's keep the last one in for now. And because if I didn't fix that, I'd have that last one. There we go. So that multiplies, what does that multiply now? In Kirchhoff's current law, multiplies W, so currents. So here are the currents, 1, 2, 3, 4, and 5. All I'm doing now is just like convincing you that it really is A transpose, that if I look at, let me pick that node now. If I look at that node, I see edge 1 coming in. I see edge 3 going out. I see edge 4 going out. And when I look at that second node, I look here at the second row, I see edge 1 coming in, edge 3 and edge 4 going out, multiplying those currents. And that will give, that current balance there gives that 0, right? That current balance at node 2 gives that 0 in the right-hand side. And then, of course, other zeros are here too. This is minus W1 minus W2. So I have a 0. This is with no current sources. Okay, and this one, of course, I guess I'm hoping that you say, yeah, the A transpose really was the right matrix to express in equals out, Kirchhoff's current law. Okay. Of course, by now you're probably getting blasé. You're expected to be A transpose. You don't need any convincing. But it's kind of good to see each time, because it's like, well, it's not a miracle, but it's like a miracle. It's as good as a miracle. because to get A transpose is just what makes everything right. Now, here's a question. Here's a question. This is a question worth thinking about. What are the solutions? If I only look at this piece of the framework, if I just look at Kirchhoff's current law, it's telling me, and I have 0 current sources. So let's just take that. Let me take just this piece of the whole framework and ask you, how many vectors W, how many solutions? Are there any solutions? Well, of course, there's always the 0 solution. But I always ask you, what are the solutions when 0 is on the right-hand side? So what are the W's that solve Kirchhoff's current law? Now, that's a new question. We haven't asked that before. What we asked before was the question A u equals 0. Remember, it was then A, this 5 by 4 matrix. U had 4 components. Just remind me, and I'm putting that column back in. So this is still here in the unreduced, ungrounded case. Just so we get started, remind me what the solutions U were for AU equals 0. 1, 1, 1, 1, or any multiple of it. A whole line of vectors, C, 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 any constant C. Okay, so there were 4 columns, but only 3 were independent. Okay, now I've made them into rows. So now I have 5, and I made the rows into columns. So now I have 5 columns. What I'm leading to is I want to count in advance how many W's I should be looking for, and then look for them. Okay, so the first question is, how many different solutions W? First of all, are there some solutions? Is there a solution W, other than 0, of course, to this system? Well, as we said last time, we've only got 4 equations here. We've got 5 unknowns. Of course, there's at least one solution. If I have 4 equations, 5 unknowns, I can do elimination, whatever systematic procedure you want me to do. In the end, I'm going to find a solution. Now, I might find more solutions. So that's the question. So now this is that key fact of linear algebra, which is, it just tells us the numbers of everything. So this told us that there were 3 independent columns of A. Now for that key theorem, which tells me that how many independent rows of A are there? 3. That number is equal. I just want to say, that's a pretty remarkable fact. You know, if I have a 50 by 80 matrix, and that 50 by 80 matrix has 17 independent columns, then this great fact tells me that there are 17 independent rows. And if those 50 times 80, 4,000 numbers are random, boy, you can't look at it and see what are the independent rows. But if you know there are 17 independent columns, then there are 17 independent rows. So what does that mean here? That means that out of these 5 columns of A transpose, which were rows of A, 3 are independent. So just tell me how many solutions I'm looking for. Before I look for them, how many so the number of independent W's, independent solutions, will be what? What's your guess? 2. 2 is the right guess. 2, because I have altogether 5 unknowns. I subtract 3 equations that are really there. I have 3 real equations here, even though it looks like 4, and I get 2. So that general picture is N. Oh, I'm sorry, it's actually M, because I'm doing the transpose here. So it's M W's minus R, the rank. So that's M is 5, the rank is 3, and this counts the number of independent solutions. So it's a nice, right, that's couldn't be better. It's a fundamental count of how many solutions are there. You're really taking the number of unknowns, 5, and you're subtracting the number of equations that are really there, 3, and that leaves you with 2 solutions, which we will have to find in a minute. Can you see why there are really only 3 equations there? Why do I say that fourth equation is not contributing anything new? I believe that fourth equation is a consequence of the first 3. And therefore, if it's there or if it's not there, it's not telling me anything new about in equals out. In other words, if I have a closed system, closed because it's 0 on the right side, if I have a closed system and I have in equal out at those 3 nodes, then I'll automatically have in equal out at the 4th node because the total in is 0 and the total out is 0. So if I'm right at 3, I'll be right at the 4th one. And now just tell me with the numbers, how would I get this equation W4 plus W5 equals 0 from the first 3? Well, it's probably the same way that I got that column was connected to those columns. What do? Add them. Add them. If you add that equation to that equation to that equation, add those 3 equations, what happens? The W1s cancel, the W2s cancel, the W3s cancel. This says there's a minus W4 and a minus W5 that adds to 0 plus 0 plus 0. Minus W4 minus W5 equaling 0 is the same as plus W4 plus W5 equals 0. By the 4 equations add to 0 equals 0. That's what the central thing is. The 4 equations add to 0 equals 0, just the way the 4 columns up here added to the 0 column. Okay, so we got the count. Now, this is the interesting part always. What are the solutions? What are the actual W's? Okay, you could say, wait a minute, you're asking me to solve 4 equations in 5 unknowns and just say what the answer is. Well, normally that's not reasonable. But here we can get help from the graph. Let me give you an idea here. So what are we looking for on the graph that solves it? We're looking for a bunch of currents that balance themselves, right? We've got 0 on the right-hand side, so we're not getting any help from outside. How could you send current in this loop in a way that would satisfy Kirchhoff? He'd be happy. The balance law would be true. Okay. The B, I'm just looking at currents. Current W1, W2, W3. Well, is there any combination of W1, W2, W3 that would balance itself, that would make Kirchhoff okay? Well, here's the idea. Send that current around a loop. Loop currents are solutions to Kirchhoff's balance law. If I send an amp on that edge, and backward on that edge, right? It's around a loop at every node. It's totally okay. So I believe that a particular solution will be for these things to be, let's see, what did I say? W1, I'll send 1 around. W3 will be a 1. W2 was backwards. It wasn't traveling on W4. I think that's a solution. That loop current gives me a solution. So let me call this solution, well, I don't know. That's a first solution. And if we do these multiplications, of course, it's going to come out right. Okay, so that's solution number 1. a W that works. Okay, with that hint, tell me a second W that works. In fact, since there are only two, you'll be giving me the rest of the answer. So that was a loop current that went around that loop. Tell me another one. Well, we're a big class, but everybody's seeing it. How about around that loop? Okay. So that would be another thing, and it's pretty clearly not the same as this one. So I'm really, truly finding two independent solutions. And what is that second solution? Let me maybe just put it in here, and they're both giving me 0, 0, 0, 0. And now what is this number 2 solution? Loop number 2. 1 and 2 are not involved now. Number 3, see, I'm usually sending it counterclockwise. That's a sort of convention, but you know, of course, you just have to follow some convention in connection with the arrows. So that would go backwards on 3, I think, forwards on 4, and backwards on 5. So that would be solution number 2. Okay. Now, tell me what all the solutions are. I found two particular solutions, two particular loop currents, particularly easy. What would be all the solutions to Kirchhoff's current law, A transpose W equals 0? Every W now, since I found the right number, every W will be a combination of those two. Well, wait a minute. Have I got them all? I should have thought, what about current around the big loop? That would certainly satisfy Kirchhoff, right? Plus 1, 1. So why is this not number 3? Around the big loop, I have a 1, and then a 1 on the 4th position, backwards on 5, backwards on 2, and so so I'll put number 3 with a question mark. What's up with that guy? You know, unless mathematics has got to close up shop, this better be a combination of those. And of course it is. If I send something around the top loop and something around the second loop and add them together, they'll cancel on the middle edge there and produce number 3. So this is probably just the sum. If I add that one to that one, I think I get number 3. So number 3 is true. It's a solution, but it's not a new one. Okay. That was simple, right? Once we saw that loops gave the answer. But it's quite important and appears everywhere. In fact, the theory of electrical networks, current laws and so on, I mean, that used to be a basic course in electrical engineering. There was a text by Professor Ernst Gilliman, I remember. It's sort of not so central to the world anymore. And now, but the structure is just right somehow. And what I wanted to say is, you could take, in those days, you maybe took loop currents as the unknowns. You could think of currents in the loops as your principal unknowns. We don't do that now. But, it comes up again. Yeah, knowing all the solutions to A transpose W equals 0, well, you'll see, what's ahead. It will be the continuous analog of this, where I have flows not just around a graph, but in a region. And Laplace's equation is going to come up, and the equations of divergence and gradient, all that great stuff is coming in chapter 3. And this is somehow the discrete case. these loop currents, that has something to do with the curl. And these differences here, these differences that A takes, has something to do with gradients. And this Kirchhoff's current law has something to do with divergence. Can I just say ahead of time, what we're doing is really good to see and get it, because then you have a way to understand vector calculus. This is discrete vector calculus we're doing here. Okay. Now, it's just right. Forgive me for my sermon there. All right. Now, may I bring the pieces together finally? May I bring the three steps together into, well, first you would say bring them into one equation. Put the three steps, combine the three steps into one. Okay. So what happens if I do that? Okay. I take that last step, A transpose, F is A transpose W. So now I'm going to get one equation, which is the equation that is going to have the stiffness matrix in it, A transpose CA. It's the equation, or maybe I should say conductance matrix today. And it's the equation that a big finite element code, a big circuit simulation code, it's the matrix they have to find and work with. You know, and those codes are enormous. And SPICE, by the way, is the sort of grandfather of circuit simulation codes. Somebody at Berkeley had the sense to see, hey, we've got giant circuits now. You know, modern circuits have thousands of elements. And you can't do it by eye the way we can do this one by eye. You got to organize it and write a code, and SPICE is the start. So one way to do it is to end up with one equation. So that was F equals A transpose W. I'm just assembling the whole loop, but W is CE. So that's A transpose CE, but E is B minus AU. Right? Nothing new there. Nothing new maybe except that it involves both the F and the B, where our earlier examples involved either an F in masses and springs or a B in least squares. Now they're both here. So now that's my equation, F equals this, and now let me just move that to let me just recollect it. That's A transpose CA, the big thing that I wanted to see. I'll put it on the left side. And what will I have on the right side? I'll have A transpose CB. And I'll have F is now coming over to the other side with a minus F. That's the big equation. You could say that's the fundamental equation of equilibrium. And you see how it's right. It involves the A transpose CA, which we expect. Over here was the A transpose CB. Now, which problem before networks produced an A transpose B or an A transpose CB? That was least squares. And now, so that's the least squares, the B term. The B is there with a couple of matrices because B entered the problem just one step around. It had two more steps to go. It had a C step and then an A transpose step. Whereas F appears at the very end, and now it appears with a minus sign. That's different from springs and masses, simply because that's the sign conventions, you could say. Okay, so there's the equation. Okay, fine. So that's what you have to solve. And actually, I think of that as the fundamental problem of numerical analysis, how to solve that equation. More effort, more thinking goes into that than probably any other single problem in some form. Okay, and here's some part of that thinking. Part of that thinking, and another important possibility, is to keep This was like the one equation, the one field problem. This corresponds to the displacement method. Can I use words that, you know, I'm not going to use seriously for another few weeks. This would correspond to the displacement method in finite elements, in FEM. FEM for finite element method. That's the displacement method. It's the method that most people use. It's the standard method. Okay. But it's not the only possibility. And let me show you a second one that involves two equations. Because that's also very, very important with many other applications that we will see but haven't seen yet. So my two equations, I really should say two systems, because one equation, that's a vector equation, right? So I mean, I have a system of two vector equations that would go into a block matrix, and you'll see it. Okay, so I'm going to keep, what two unknowns am I going to keep? U I'm keeping, displacement I'm keeping, but I'm also going to keep what I think of as the other important unknown, W. So the other important unknown is W. So now I have two equations, and one of them is just the current law, the balance law, A transpose W equal F. The only guy I'm eliminating is E. You know, initially you could say I've had three field system, U, E, and W. Now, E and W are so easily connected that I'm going to eliminate E. E is C inverse W. I did it actually here. This W is C B minus AU. That's, we know. If I multiply by the C inverse, then I have C inverse W is, and I bring the AU over to the far left, and I have only the B left. Everybody saw that? I did a C inverse there to get E like off by itself, and then I substituted for E. I put in the U part, so E is now gone, and the equation is C inverse W plus AU equals B. That's my two-field system. Those are, yeah. Now, there's a matrix here. Yeah, this is really nice. I just want to write that. I've got to what I want, but now I want to look at it. So I think of a 2x2 block matrix multiplying WU and giving me BF. And I want to ask you about that matrix. So this is the matrix for when I've only eliminated E, and I've still got W as well as U. Okay, well, you can read off what's in that matrix. What goes up here? C inverse, of course. Positive, diagonal usually, easy. What goes here is a rectangular. That guy is rectangular. A transpose is multiplying W, so it goes down here. And this equation has no U in it. That matrix is worth noticing. And let's spend the rest of the remaining minutes just to think about that matrix. I just want to say, what if I keep W and U? This is an important possibility. And it's important in finite elements, which, as you know, is just a terrific way to solve a whole lot of continuum problems. And what's it called when I have W and U together, both unknowns, not eliminating W now? It's called the mixed method. So this corresponds to the mixed method in finite element. It corresponds to the possibility of keeping W and U. Well, and you might say, well, isn't there a third possibility? And what would that be? Keep only W. Here we kept only u. Here we've got them both. This is kind of the mother of all equilibrium equations. And another possibility would be to keep only the w's, to make the currents the primary unknowns. And that, and in the finite element structural context, that would be saying make the stresses. So of course it would be called the stress method. Be called the stress method, and Professor Pion in course 16 was one of the, now retired, was one of the major developers of the stress method. The difficulty with the stress method, the reason it didn't win big time, is that the w's, if you make them the unknowns, you've got a constraint on them. Kirchhoff's, not all w's are allowed. Somehow over here, all u's are allowed, and that made it much easier to set up the problem. So the displacement method is the 95% winner, but there are problems where maybe C inverse is too complicated or C is too complicated, and you're better to, we'll see, we can see that. That's later in the book, but we want to see now about that matrix. Well, if I wrote that matrix down, and let me write, just so you, I want to ask you about that block matrix. What's its size? All right, now just focus entirely on that block matrix, because that's what I care about. What's the size of that matrix? Let's see, what's the size of C? M by n. What's the size of A? M by n. So what do I have here? I've got m rows and m plus n columns, and there's n more rows. It's of size m plus n. It's got the NU's and the MW's, of course, m plus n, the natural size, right. So it's got more unknowns, but we'll see, in optimization, you bring in Lagrange multipliers. That's just exactly parallel to what we're doing here. You have extra bunch of unknowns. That's what we have. Now, what else about that matrix? I was going to write down a very, very tiny model for that matrix. I'll just make it 2 by 2. Here's a model for that matrix, where C is just a 1 and A is just a 1. It doesn't it's kind of laughable, right? That model, this is the real thing, but it gives you an example to check against. Okay, what's the property of that matrix? It's, again, symmetric. Good. That's a symmetric matrix. Because what happens if I transpose that block matrix? That A block will flip over here as A transpose. The A transpose block will flip up here as A. What happens to this C inverse block? C is a symmetric guy. In fact, it was just diagonal in our imagination. The key point is it's symmetric, its inverse is symmetric, its transpose is the same. So that's a symmetric matrix. That's a good thing, right? Now we've got a matrix that's symmetric, square, symmetric. Okay, what's my other question about that matrix? Is it or is it not positive definite, right? We got to answer that question. Have we got a positive definite matrix? Would all the pivots be positive? Would the eigenvalues be positive? What's your guess? No. That matrix is not positive definite. No way that a matrix with a 0 there, a 0 block, or that matrix with a 0 number could be positive definite. No way. The energy in this guy, this U transpose AU, you remember, would be U1 squared and U1, U2 twice, and no U2 squareds. And that thing is definitely indefinite, right? You know, in the U1 direction, it looks good. That's things positive there. But if I took U1 and U2 to have opposite signs and made U2 big enough, then of course this just brings it down. So the graph of that would be a saddle point. The graph of that would be a saddle point. Okay, and now here I have the same thing on like a m plus n size. So what do I have? Actually, what you could see here, the last exercise is mentally do elimination on that matrix. Mentally do elimination on that matrix. So start with the first m rows. Elimination, you know, we'll work with those first. What will elimination do? What will the pivots be like? What will happen at the beginning of elimination when I start with this matrix? Well, it meets C inverse right away, that diagonal matrix, and it's extremely happy. Those will be the pivots, right? They're sitting on the diagonals, 0 off the diagonals. There'll be positive pivots. I'll have m positive pivots here, m positive pivots. And then I get down to where A comes in the picture. So on the last board here, let me just copy this matrix, C inverse A transpose A 0. And elimination is going to, it'll be very happy with that, but it's going to so it's happy with that row, block row. It's going to do an elimination to get a bunch of zeros there. And what did it do? This was elimination, this was subtracting. Yeah, what did it subtract here? It multiplied these pivot rows by something and subtracted from these lower rows and got the 0 block. And what did it multiply by? What do I multiply that block row? And this is a perfect exercise to see how blocks are just like numbers. You can deal with them. What do I multiply that block row by and subtract from the row below to get a 0? You said CA transpose, but I don't think that's it. A transpose C. You got to multiply by A transpose C. First of all, CA transpose wouldn't be a possibility. Wrong shapes. A transpose C is the 4 by 5, 5 by 5 guy. So you multiply A transpose C, that cancels that, leaves the A transpose. When you subtract it, gives you a 0. And what does it give you there? What shows up there? A transpose C multiplies that A, subtracts. So it's actually what shows up there is minus A transpose CA. Let me write it in there. Minus A transpose CA. So that matrix is exactly what comes from this one. It's exactly what we do when we eliminate W. That's what elimination is. I just eliminated W by getting a 0 there. And I got only an equation, but notice the minus. So final question. What are the signs of the last n pivots? The first m were all positive and they were sitting on the diagonal already. The last n are not so easy to see, but we can see what sign they have. And what sign do the last n pivots have? Minus, because they come from a negative definite. Minus A transpose CA is shown up there. So that's the saddle point. Saddle points are, when you have two field problems, you're talking about saddle points. And the mixed method in finite elements is exactly that. And the tricky part is then, with the mixed method, you're sort of not so perfectly guaranteed that the matrix is invertible, because we have plus stuff and minus stuff. Okay, thank you. That's great. And I'll see you Monday, all about the exam and review. It's a great chance to think back. Thanks.